Hello, good afternoon. I know some of you have signed up, and then can you hear me clearly? I just want to check. Communication is right. Hello? Hello? Okay, can you see the screen? Okay, all right. So, just want to make sure if any glitch. Any questions before we start class? Yes. What is what? Oh, this week's lab. I don't have further the instruction from the UMBC, the COVID team. So we will continue to be online. I already instructed TA, so I hope they have communicated to you, but should be shortly. Yes. Yeah. Mm. Other questions? Okay. So no question. So let's start the class. Before I run into today's subject, I want to quickly chat with you guys. I said I'm going to give you some review on the first exam and either class time or additional time. And right now I'm leaning towards give a review on a separate time. So pulling you guys, would this Friday be good time? Around noon. Hello? Hello? Can you guys hear me?
Yeah, we can hear you.
Okay. So then I was around noon time. So maybe start at I don't know. Could be 11, could be 12. I will decide later and inform you from the blackboard. Okay.
Okay.
Review for the exam. Yeah. So I'm just I can give you some guidelines how to study and what are the important things. And you guys, if you have any questions, you can raise the question to me. I'll try to address that. Okay. Yeah. Okay. So no further questions. So let's go back to our class lecture. So last class, we introduced bipolar junction transistors. So this is this is the second slide. There are two types of bipolar junction transistors. One is made of NPN street region material, NPN. So this is a illustration, graphic illustration of street regions. And on the left side is the emitter. In the middle is the base. On the right-hand side, that material region is the collector. Okay, so it's N material, P material, N material. So there are two interfaces between there are two interfaces. One is between the emitter and the base on the left interface, and then there's another second interface on the right between the base and the collector. Okay, and most important operation region is what we call the forward active mode, and this is illustration for NPN bipolar junction transistor. The condition is regardless whether it's made of NPN or PNP, they are highlighted in the blue. Okay, said the condition for forward active mode is between the base and emitter junction, that PN junction should be forward biased. Between the collector, base and collector junction, I call it BC junction, must be reverse biased. Why? Because because the emitter is most important because you have a mostly doped material region, so a lot of charge carriers coming out from the emitter. So in order the emitter to get across the PN junction on the left, get into the base, you need that junction before bias. So we learned from the dial. That's what is important. If you want to inject the majority carriers from the emitter into the base, that junction must be forward biased. The second junction must be reverse bias. So under reverse bias, you have a very strong space charge field, okay, on that second junction. And that space charge field, normally you block the current. However, under the injection of the carriers from the emitter into the base, and once it diffuses across base, those carriers will be swept through the second junction, get to the collector. So important thing is, okay, if you have a large collector current, and that second junction must be forward biased. Must be reverse biased. So this is the graphic indication. Okay, if you want to have a lot of majority carriers injected from the emitter to the base, the first junction on the left should be forward biased. And if you want these carriers further be swept to the collector through the second junction must be reverse biased. Any questions for this basic operation principle? If no, and this is a PNP, okay? The principle is similar, it's just an electron and hold the rho exchange, and then the power supply voltage will reverse the polarity, and directional current actually flow the opposite way because the charge changes from electron to hole to electron. Any question? So no question? So
Professor, can you just stay on that slide a moment? I'm trying to follow which way the current flows in that diagram.
Which one? This PNP or NPN you want?
NPN.
NPN. Let's go back. Okay, is this good enough?
I was hoping for the other diagram.
Okay, no problem. Flip this. Yes.
Yes.
The electron inject from the emitter to the base. Because electron has negative charge, so the emitter current is flowing the opposite direction. Similar to the collector. Okay, electron going this way, but the collector current going this way. Any question? Hello? I hear some echoes, not clear.
هیچکس حرف نمیزنه، فقط دو نفر حرف میزنن. چرا این هلو میکنید؟ مستعد باشید جواب حرف بزنم میزنه.
Cameron, your mic.
Is this a class discussion? Okay. Did I answer the early question?
Professor, so for the NPN, in the state where this is forward bias and reverse bias, is on B, is current flowing in or out?
On B, right. That one is the textbook that doesn't show that direction of current. But that's why I refer you to the next graph. It's very clear. Just lay out where those carriers originated from where, and they flow to what direction, and corresponding the current. Is it clear? I think the second graph is more clear in terms of where the charge carriers move and where the associated current direction are. Did you see that? Hello?
I'm afraid I'm still not following. When you have current flowing through here,
From where to where? Can you tell me? Refer which current you have in mind?
Current IB1.
IB1 are the holes, okay, originated from the base because of the P material. There are a lot of holes in the P region. And that PN junction is forward biased so that the holes will move from the P region to the emitter's N region. That's as indicated there, IB1.
So when we do have holes flowing there, will the transistor be open or closed?
Open is under forward bias, forward active mode.
Okay, thank you.
Yeah, that PN junction is open, okay, to allow the majority carriers to move. Okay, that's the diode's property. Okay?
Professor, I have a quick question.
Yes.
Could you, I don't know if I missed it, but could you tell us quickly what the format for the exam is going to be? Like, do you know yet?
Well, let's defer that to my review section. All right?
Okay.
Okay, Friday I will answer those questions. Okay?
Good. Yeah. Thank you.
Okay.
Professor,
Yes.
sorry, but on the exam, just about, you said we're going to put it off until Friday, but is the exam Friday?
No, exam is the Thursday the next week, October 1st.
Okay.
Okay? So Friday you still have 6 days to study for the exam after my review. Okay? Good enough? Okay, so let's look at the transistor circuit. And then this is a transistor symbol, the NPN material, and then the circuit symbol, PNP structure, and then corresponding to circuit symbol. Okay, one on the left, one on the right. So this is the first transistor circuit configuration. We use NPN, bipolar junction transistor. And left illustrate the full circuit connection. You use one NPN transistor, the two resistors RB to the left, RC on the right, and the two power supply voltage. One is on the base side, is called the VVV. The other one is connected to the collector side, is VCC. Okay, and to the right, I further just create a figure myself. Let you visualize that the transistor internally is NPN structure. I lay out there. Okay, just one-to-one layout. Any questions? If no questions, so let me just switch to a different graph. So I need to discuss this based on the configuration. So I illustrate that diagram to the left. Okay, on the right, I have to scroll to the second page. But second page is more concentration on what happened, within the bipolar junction transistor. So you follow the statement I wrote down here. I'm discussing the current and voltage relationship, and the current is collector current, IC, and the voltage I refer to importantly is the VCE. VC stands for the collector, E stands for the emitter. So that's the voltage between the collector on the top and emitter at the bottom. And that voltage is VCE. Okay. So this voltage VCE. I'm looking for the current IC related to voltage VCE. And you refer to the left. Okay, if I have a bias voltage VBB, if this VBB is sufficiently large, then the voltage between the base and emitter will be more than enough to above the threshold voltage. And that threshold voltage in a diodes context, we call it V gamma. And here in the bipolar junction transistor, the terminology we call the VBE on. So the first bullet said on right hand side, if the bias voltage is greater than the VBE on, then B junction is full bias. Once full bias, then you create a base current. That BN junction is on. You create a base current, this current. Okay. Let's say that between the base and emitter is a full bias. And how do we create a reverse bias between the base and collector? So you will refer to the left. If the voltage VCC is more than voltage VBB, then the second junction between the base and collector is reverse bias. So the VCC greater than VBB and base collector junction is reverse bias. The total voltage drop between the collector emitter can be expressed into the sum of the two parts. So first part is between the collector and the base, and second is the part between the base and emitter. Okay, so that's the formula. And that formula, because base emitter, the junction is a full bias, that's positive, so that the sum of the two terms must be more than the VCE will be greater than VBE. So that's the case, then the VBC will be negative, so the reverse bias. So we satisfy these two conditions. When the power supply voltage VBB greater than VBE on and VCC greater than VBB, okay, we satisfy the two conditions for forward active mode. In that case, then the collector current will be linearly proportional to the base current IC equal to beta times IB. So the second condition is only when we are running in the forward active mode. Now I look at the situation, the base side condition doesn't change. So you have a given base current. Okay? You have a given base current. However, if I reduce the voltage of VCC, okay, so the vertical arrow just say I intend to reduce the power supply voltage VCC. Well, looking for the second bullet. Second bullet say if VCC greater than VBB, the BC junction is reverse bias. But if I reduce VCC further to below VBB, then we know the BC junction will become forward bias. Okay, here I give an example. Okay, number VCC equal to VCB plus VBC, and VB is diode, the junction is a turn-on voltage. VB is 0.6 volts, for example. And if VCE reduced to 0.3 volts, then VCB will minus 0.3 volts. That means it's a reverse bias, it becomes a forward bias. Well, because it's forward bias, then you don't have a space charge field to pull the injected carriers from the emitter into the base, and they cannot get to the collector. So that tells me the final statement. In that case, collector current will be drop until 0. Okay. So all these three bullets is summarized by the graph I created. Okay, I plotted the vertical is collector current, horizontal is VCE. Okay, the red line is given the base condition doesn't change, I create a certain amount of base current, and the current IC, I have a portion of IC beta times IB, but if horizontal axis VCE get too small, drop to the around the 0.3 volts and so forth, that IC start dropping down, eventually dropping down to 0. Okay, so this is the single curve telling me if the base side condition unchanged, if the base current is fixed, then the IC depends on VCE. When VCE gets too small, will drop to 0. And what happened? If I increase the VBB, the voltage, if I increase the VB voltage, then the current IB will be stronger. So IB will increase. But for given IB, I have the same set behavior for the IC. So that gives me the graph, the first page, the previous page, say I have a family of line. Okay, each line corresponds to a fixed base current, but IC almost stay constant until it drops to 0 when VC goes to too low. And the next one, I have large IB, then IC will be proportionally large, but eventually also drop to 0. Okay, third line says I have an even large IB, but IC will eventually drop. Okay, so in this, before it drop to 0, then that region we call the forward active mode operation region. Any questions? So that family line of curve is summarized, okay, from textbook is printed here. And we notice that, okay, and here I make statement. In forward active mode, the collector current is proportional to the beta current. So given base current, IC should be constant, right? We just say that line should be constant. Why there's a slight tilting? Well, that's the next slide telling me the effect. Next slide says that's the effect or the phenomenon is called the early voltage effect. Based saying all the given a IB, I have one curve for IC, I have another curve for IC for different IB, I have a third line IC curve for different IB and so forth. They tilt, but if you extrapolate to the left-hand side, they all join a single point. So that's early point, so early voltage point. And that early voltage is, in terms of the measurement of voltage is a minus because it's negative, but the magnitude is VA, that's VA. So early voltage, called the early voltage is VA. Why that happen? Well, then we have the trace, okay? What makes this line not flat, but slightly tilting? So I will explain this way. Consider, so this region, I have a smaller VCE, and here I have a larger VCE. I need to explain why larger VCE will help increase collector current. So that's the statement here. Okay? Larger VCE provide a stronger reverse bias on the BC junction, right? So larger VCE means that this voltage is large. This voltage is large, but the left side, this voltage is fixed. If this voltage is large, then the reverse bias voltage between the base and collector should be stronger. Well, the consequence, if the reverse bias condition on the BC junction is stronger, then the space charge region by itself in that intersection will be expanded, become larger. And consequently, the base width will be slightly shrink. And that make diffusion, from the diffusion of majority carrier from the emitter cross base is easier. So because cross base is easy, it means that they can better to get into the collector. So collector current is slightly large. So that explains that is slightly large. Not a drastically large, just slightly large. So we have these tilting curves. However, these all tilting curves, if you extrapolate it, they join a single point. So this is a linear behavior. So how do we model this linear behavior? So we modify the collector current. So collector current has the first part just saying is alpha times the emitter current. So that's usually we say collector current is not a beta IB, but alpha times IE. So delta times IE, the first part. Well, how do we modify this slight linear dependence on VCE? There's a second term inside the parenthesis. So it's the VCE over VA. So that's a linear term. So if VCE is 0, then there's no correction. Oh, VA is infinity, then the second term is 0, doesn't contribute. So what we're saying, if the VA is infinity, then we're saying we neglect early effect. Graphically, you can see that if a VA is pulled negative infinity, or this line will become sort of a flat. And then this will be flat. So that's where the flat IC current, just proportional IB and IE. But putting this small term, VA may be on the order of 50 volts, 100 volts. So this is small correction. Small correction says it's a linear increasing. Linear increasing just indicated there's a slight increasing tilting of the curve. So this is the collector current is modified by the second term inside the parenthesis. Any question? Okay. So let me just make a restatement on this, the early one. So this slide page 5, the second bullet, we said that collector current, in forward mode, collector current is proportional emitter current. So that's constant, doesn't depend on any voltage of a VCE. So suppose the IC should be flat, straight line, horizontal. But once we modify this constant collector current, then we modify this by this equation. So by this equation. So there's a second term modified. The second term modified, this is a linear increasing of IC was VCE. Any question? Okay. So previously, we discussed that using the NPN transistor configuration. What if we're using PNP transistor? So the left side just indicate, this is still the base, emitter still connected to the ground, and collector is still on the top. And the resistor, there's a resistor RB on the base side, and there's a resistor RC connected to the collector. Because we use PNP transistor, we said the role of electron hole exchange and also the external bias voltage, we flipped polarity. So VBB, we flip the polarity. So plus polarity connect to ground, negative polarity connect to the base. Likewise, the polarity of VCC exchange flipped. Plus side polarity connect to ground, next side polarity connect to the resistor RC, and then eventually get to collector. And also the current direction flipped. IB will get out, IC will get out, but IE gets into the transistor. So this is if we are able to flip the power supply voltage, or to the other way to say, if we can supply a negative voltage source, then we can configure the PNP transistor, indeed the left side configuration. And then, in the writing, I said with a negative power supply voltage, then the two conditions, how do we satisfy for forward mode? So the base emitter junction must be 4 bias. So 4 bias, this is, we need the VBB, the voltage still greater than VBE on voltage. So that PN junction between the base and emitter is 4 bias. And we want this junction be reverse bias. Again, the magnitude of VCC must be greater than magnitude of VBB. Okay. That's when we have a negative power supply voltage available. We can configure or connect the transistors and power supply voltage, okay, according to the left side, okay, diagram. On the other hand, very often the available, okay, voltage source are positive voltage source. Okay, many of the power supply only gives you an output positive voltage source. Okay, difficult to get a negative voltage source. But how do we power the PNP transistor with positive voltage source? Okay, this is a new configuration. So new configuration, actually, the base is still in the middle to the left. However, the collector through the resistor is connected to ground, and the emitter we put on the top. And we use a positive power supply voltage VBB to connect between the ground and the base. We use another power supply voltage, positive voltage, connect between the ground to the emitter. All right, so that's the configuration. But we need to verify or identify, okay, under what condition any PNP transistor is operating in forward active mode. So this is the second part of the statement. So with positive voltage sources, how do we create a B junction before bias? Okay, there you can see that my statement says that VCC subtract VBB must be greater than the PN junction VEBR. Why? Graphically, you can see this on the right is VCC. It all come from the ground to the top collector. VBB is the ground and get to the base. If this voltage on the top is more than this voltage, more than say 0.7 volts or VEBR, then the collector, not this collector, this emitter, I don't know, I made a mistake statement say, this is emitter, not collector. So if VCC is more than VBB by amount of EBR, this PN junction will be forward biased. If this PN junction forward biased, then the base emitter junction is forward biased. So we satisfy one of the conditions. The second condition is this, okay? The base collector junction must be reverse biased. Well, if a VBE is positive voltage, then this junction is reverse biased. We satisfy the second condition. Okay. So with either situation, we can make the PNP transistor to operate in forward active mode. Any question? Okay. And this is another configuration. We use NPN or PNP transistor, but in this configuration, there's a current source involved. And that configuration we name called the common base configuration, and here with current source. Okay, and this is a family line of current IC versus voltage. Let me just expand to 100%. I hope this is larger. The current IC versus voltage VCB has this family line. This is very familiar, similar to previous line, except okay, in forward active region, that line is flat. And then eventually IC will be dropped zero. Okay, second feature is it drops zero not on this side, not on this region, but dropped at what? The negative side of a VCB. Okay. The important thing is that here I plot IC versus VCB. Okay. Next slide tells me what happened. Oh, this slide tells you what happened. So let me just, I still have to use the diagram to the left. Okay, refer to this diagram. Shrink a little bit. Okay. If it's a forward active mode, we must make sure, okay, between the base and emitter should be forward bias. Okay, so let me turn on. Sorry, cannot get the cursor moving. So between the base and emitter should be forward bias. How do we make that happen? Well, that's the writing on the right hand side. The condition 1, there's 2 parts. Base emitter junction is forward biased if the negative voltage V minus, so this bottom voltage, negative voltage is low enough, and then this current direction is pointing down, and current is positive. If current pointing positive, if the V minus is negative enough, it will drag the location, okay, the potential at the emitter is sufficiently below the ground. If this voltage is sufficiently below the ground, then this junction will be forward bias. Okay, so this. How about this junction be reverse bias? Well, obvious. This voltage V plus, and this is 0 ground, and you have a positive voltage between the collector and base. So this junction is reverse biased. Okay, just confirm. Okay, just convince you why. If a VCB is positive, we call the reverse bias. Remember, this bipolar junction system is NPN type. NPN type means what? Emitter is N material. Base is P material. Collector is N material. So this is P side, this is the N side. You put the positive voltage on the N side, you put the negative voltage on the P side, that PN junction is a reverse bias. All right? So that is, okay, statement 1B, make that a statement. And second one says, now we can operate the transistor in the forward active mode, but once you operate in forward active mode, all the currents are linearly proportional to each other, then the collector current IC is proportional to IE. And alpha is almost equal to 1, 0.99 equal to IE. So IC is tied with IE. So it's a nearly constant current source because IE is, this emitter current is tied with the current source. If IE is constant, the emitter current is constant. So emitter current is constant, then collector current is constant. So that's why the collector current IC is constant flat. Okay. Why is dropping not appear on the this side of diagram, but on the next side diagram? All the reason is I'm plotting IC versus a VCB. Okay, see if I can enlarge this one. I'm plotting IC versus VCB. Okay, so what's VCB? So the horizontal axis actually is shifting. I'm not plotting VCE. I'm plotting VCB. But what's the difference between VCB and VCE? And VCB equals VCE minus VBE. And VBE is constant voltage on 0.6 volts, for example. Okay, so here I have a numerical example. So what's the amount of VCB when VCE lower to 0.3 volts? Lower to 0.3 volts, you subtract VBE on 0.6 volts, you get a minus 0.3 volt. So this is the minus. It shift to the, on the diagram was VCB. Then the IC drop to 0 is occurring at minus 3 volts, 2 volts, 3 volts. Okay, so that's a V, and under this condition, VBC base collector junction, we know it's a remain 4 bias. However, when it's a 4 bias, then we don't have a strong electric field to swap the carriers into the collector. So the collector current will drop to 0 as well. Any question? And here probably you notice that, okay, I put in the words VCE set equal to 0.3 volts. So what's VCE set? Okay, VCE set is in this diagram. Okay. In this diagram, early voltage effect, okay, is between the forward active mode, the border, to the 0 of a VCE, that gap is a VCE set. Okay, later I would explain that phenomena, okay, as well. Okay, so this separation is a VCE set. Okay, so that means that when the VCE dropped the VCE set and the current started lower to 0, and that's for the common emitter configuration. For the common base configuration, okay, the horizontal axis will be shifted by a constant 0.6 volts. So it's from 0.3 volt, and shift down to minus 0.3 volt. So that's a shifting. Any question? So these are the basic.
I have a question.
Yes, please.
Okay, for these devices, what are we using them for?
Later we will see transistor amplifier.
As a current amplifier?
Both. There's some situation we have current amplification. There are other configuration we can make it as a voltage amplifier. So the transistor can be put into different configuration to serve different type of amplifier purpose.
Okay.
Okay. So we will learn that. Particularly, we learn that in chapter 6. Okay. Chapter 6 deals with the amplifier. Chapter 5, okay, learn the basics of the bipolar junction transistors. Any question?
Professor, I'm sorry,
Yes.
I'm just not following how we're making an amplifier out of this. For this graph, we're graphing when you have 2 points connected and the third point is connected to the ground?
Let's go to the familiar one with the NPN transistor. You're saying this one?
Yeah, one of the leads is connected to ground. So how do you get an amplifier out of this just from a power distribution point? Because we're just passing, the current's going to go through it, and there's no source of power here. How can this amplify any of the elements?
Let me correct you first. What do you mean by no source of power?
Well, when we're talking about, like in 306 with a voltage source or something, we're talking about a function that, in addition to getting inputs and outputs from the circuit also has connections to voltage and ground, so that it can introduce more or less voltage into it depending on the exact component. So I'm not following. There's no more power sources here. The transistors can connect to a power source. So how are we using it to amplify?
Okay, question. This is a basic configuration, but this is still not yet to talk the amplifier. Particularly when we say amplify, you say amplify, particularly we talk about the AC amplifier or analog signal. Okay, so the signal as time going up and down, up and down. So that means there is a AC source will be introduced into circuitry. So we are saying amplify, we amplify the AC signal. The DC signal here is a battery VVB and battery VCC will serve the purpose as your power supply voltage for your operation amplifier. Your operation amplifier, you have the power with a V plus and V minus. This will be similar function. Again, right, this configuration doesn't tell you where the amplification occur, but chapter 6 will explain. In chapter 6, we'll introduce AC source, AC signal in, and then we'll see how AC signal is amplified. Did I answer your question? Hello?
I mean, your answer was wait till chapter 6.
Huh?
Your answer was wait till chapter 6, right?
Correct. Because chapter 5 only say you operate the transistor in its middle point based on the DC voltage. And the middle point, or we call that, in chapter 2, we call the quiescent point or bias point. And around the bias point, okay, you inject the AC signal, and you see the AC signal gets amplified. And that part discussion, indeed, is in chapter 6. Okay. So the chapter 5 only say we operate the transistor at a fixed point. Like on the fixed voltage VBB, bias voltage VBB and VCC, transistor indeed operate at a fixed point. You don't see input signal to be amplified to the output. Input signal to be amplified output is addressed, discussed in chapter 6. All right? Okay? Answer your question, right? Indeed, if you want to see how amplify is working, operating, you have to wait until chapter 6. Okay. All previous one says transistor operate normally. Okay, so ideally. And the other configuration, transistors, okay, may not connect, okay, under ideal condition or under correct conditions. So in that case, we have a non-ideal situation, and we may have the current we call the non-ideal leakage current. So this slide, okay, so let's focus on this slide. Says one is open emitter. So to full forward active mode, so let's refer to this, the original configuration, forward active mode. Right. This is a full configuration, forward active mode to the left. To the right, well, what if I remove the bias voltage VBB? So I remove the 1 voltage power supply. So the emitter become open. So that's open emitter situation. So once you have open emitter situation, then the base emitter junction is not biased. However, the base and collector junction is reverse bias, as we said, reverse bias. Well, this PN junction reverse bias, what you have is you do have a current, and that current we call it VCBO. CB means the current between the collector and base. O stands for open circuit, open emitter. And that amount of current is called IS. That IS is what we learn, okay, the dark current or reverse bias saturation current for this PN junction. All right, that's purely the chapter 2's knowledge we learn. Okay, so once the emitter is open, all we can focus is between the base and collector. That PN junction, what happened? The second situation is I do connect the voltage to the emitter and the collector. However, I break the base. So the base is open. Right, there's another configuration possibility. So basically, you hook the transistor, you forgot, okay, to hook up one terminal one way or the other. In this case, suppose we let the base open. So you do have a voltage applied between the collector to the right and the emitter to the left overall. So you would expect there's some sort of current flowing this way from the collector and going to emitter and come back to the power supply negative voltage side. Well, here I list a few currents involved. First is current ICBO. This current is the same amount of current. This current is what? From between the collector and base under reverse bias. If under reverse bias, they're coming from the minority carriers, as we learned, from the chapter 1. So that's one contribution. Current under reverse bias, minority carriers moving around across this barrier that contributed to this current ICBO. There's a second part of current ICO between that's this current. Because what? If you put this side is a positive, collector side is a positive voltage, emitter side the negative voltage, then the second this PN junction on the left hand side is more or less forward biased. So once you have a forward bias, you do have a current, which I call the ICO. So these are the majority carriers, contributed from the emitter and base, because the emitter base junction is forward bias. But once this junction carrier is forward bias, you have this carrier, some of this carrier can be swept by this strong space charge field into the collector. So if alpha times this amount gets to the collector, so a portion of ICO, how much portion? Alpha times ICO will be the current existing between the base and collector. So that's the second part. Of course, these two parts sum up equal to ICO. So that's a mathematical equation I have. And from here, I can work out this equation, find the solution for ICO, which is related to ICBO divided by 1 minus alpha. And approximately 1 minus alpha is beta. So the beta times the ICBO. And that just says the dark current or leakage current here is ICBO, IEIS is 10 to the minus 15 amps. But you're talking about this current will be stronger. How much is stronger? About the beta times stronger. Still, it's very small, Yes, it's about 100 times stronger in the second situation, but nonetheless, you times 10 to the minus 15 amps times 100, that's still leakage current. So this is one type of situation, non-ideal. And second is a more important situation, a breakdown occur in reverse bias BC junction. We know that we want to operate the transistor in a normal way, so we need to satisfy the 4 active mode condition between the base and emitter. Between this base and emitter should be 4 bias, but between the base and collector, this should be reverse bias. And we hook up all the terminals correctly, so we are running into full active mode. Good. However, that just says, keep in mind, a second PN junction, between base and collector is under reverse bias. What happened if this voltage VCC is too strong? If it's too strong, this base collector junction is a reverse bias, then reverse breakdown can happen at this PN junction. Once reverse breakdown occur, you can generate a lot of carriers by breaking the covalent bonds in this PN junction, and you have a lot of additional carriers available, and you create a big curve. So that's illustrated in this curve. You increase the VCC, so the horizontal axis, you go further, but boom, at some point you hit a reverse breakdown at the BC junction, then this current just shoots up. And that's not good. You don't want running into this situation. You want the base collect junction be under normal reverse bias situation, but not hitting the reverse breakdown region. Okay? So the statement is avoid. You need a base collect junction be reverse bias, but you want to avoid become reverse breakdown. Any question? No question. So we discussed actually up to this point. We discussed the bipolar junction transistor, the physics basics, the basic property, basic features. From slide 16, now we formally try to analyze the transistor circuit. Okay, so here again we replot this transistor circuit configuration we call the common emitter circuit. An example is using NPN transistor. So common emitter refers to, as this diagram, the emitter is connected to the ground. So that's a common emitter configuration. Common emitter. But circuitry connection is the same. And here, once we learn, in forward mode, the feature or the property of the transistor, then we know we need a forward bias, the base and emitter junction. And this is PN junction. So between the base and emitter, we can model this junction by the diode PN junction. So between the base and emitter is modeled by a diode. And the diode turn on voltage V gamma, right now we call the VBE on. Any questions about this? So let's get the diagram a little bit bigger. Okay. So
I have a question.
Yes.
So I still don't understand what this device is doing.
Be patient. Okay. Let me just let you just refresh back. Okay. In the diodes, we discussed two chapters. First chapter, chapter 1, chapter 2. In chapter 1, we learned the basic diode fundamentals. Okay, it's a material structure, and you hook the voltage in one way, it behaves a certain way. You hook the voltage in the other way, reverse bias, it behaves the other way. If you hook the voltage too large, you may run into the reverse breakdown, the PN junction diode. And that diode, we didn't say any particular circuits you're going to see, but just a fundamental property or the physics of the diode. But many diode circuit, application circuit, we have examined that, analyzed that in chapter 2, if you recall. So now we're learning bipolar junction transistors. similar things is here. We first have to learn the fundamental physics and properties of the bipolar junction transistors. And then we'll introduce formal different type of transistor circuits serving for different purposes. Particularly that part, okay, massively analyzed in chapter 6. Did that answer your question?
Yeah.
It looks like you're very eager to learn what kind of transistor circuits we're using and what function are they? Well, we're still a little bit early for that. Okay?
Okay.
Okay, so there's similar things happen here. You can say chapter 5 is more like the chapter 1 for the diode, and here's for the bipolar junction transistor. And chapter 6, there's a lot of applications of the transistor. You will learn a different type of amplifiers. Okay. Here we just learn how to analyze the circuit. Just like if you recall, in chapter 1, we also learn how to analyze the basic diode circuit. And here we just say how to...
Professor?
Yes.
Question on this page. Is the diagram saying that we can take this transistor and model it as a diode and a current source?
Yes, that's exactly. I'm getting into that before I answer a previous student question.
Okay.
It's similarly, how do we model the bipolar junction transistor? Okay, exactly. So how do we model the transistor? Okay, to the left is a very abstract circuit symbol. There's 3 terminals. One terminal is emitter, one terminal is a base, one terminal is a collector. And we can refer the voltage between the base and emitter called the VBE, and refer the voltage between the collector and emitter called the VCE. That's very abstract. It's circuit symbol and voltage. But here we're saying, how do we model it? Because base and emitter is a PN junction, we need a 4 bias it so that we model it that visualize as a diode, PN junction diode between the base and emitter to the left. And the turn-on voltage is called V gamma. Once turned on, that voltage is fixed at V gamma, and now we call the VB on. So when it's on. But when it's off, if you don't have sufficient voltage to 4 bias the transistor off, that means what? This part circuit is break. Transistor off, no current. So that's just modeling. Okay? That's modeling between the base and emitter. How about modeling the other branch? The other branch we say is, if we bias the transistor, okay, satisfy the 4 active mode, then the collector current IC will be proportional to IB, as we said here. Okay, the device, and this device is the BJT device law. Okay? In 4 active mode, collector current is proportional base current. We learned that. That's again, there's a transistor basics, right? And when we learn the basics, we may say, okay. Well, don't just be okay. Just say, digest that, remember that. And here we use that property. IC in 4 active mode is proportional IB. So that just says we can model the collector current as dependent current source. What's the dependence? IC equal to beta times IB. That's what it is. And this current is this current to the left, IC all the way flowing from the top to the bottom. So this branch of the current, we call the dependent current source beta times IB. The total current coming out of the emitter, IE, will be sum of the current of base current IB and collector current IC. Okay. Any question? Indeed, yes. The previous slide, they built up the basics, the ground for us to model the bipolar junction transistors. Okay. Any questions?
Professor,
Yes.
like I was saying earlier, we don't have any external inputs on this. We don't have any, the transistor doesn't have any source to power, source to voltage, source to ground.
Mm-hmm.
There's no power source. So how are we modeling this with a current source? That's a current source, right?
No, this is not a current source. No.
Then what is that?
This is dependent current source. It's not a true current source.
So it's a dependent current source.
Do you see that symbol? Is this an external current source I put into the circuit? No, I didn't put. I just say the internal transistor, there's a physical behavior. Say the collector current is just equal to the beta times base current. And that property, this property can be modeled by a dependent current source. We're modeling the transistor behavior. We are not putting the actual current source in the circuitry. Again, it's still the modeling of the transistor behavior. Did I answer your question?
I'm just confused of why is it that this can be modeled as adding power to the circuit?
You keep saying adding power. I'm trying to correct you. I did not add power. The last equation, okay, IC equal to beta IB. How do you treat this? This is a transistor property, the last equation. So that means what? The collector current is dependent on the base current by the coefficient of beta. So there's a dependency between collector current and base current. I'm just putting this dependency mathematical equation into the circuit modeling, which is a dependent current source. Hold on, please. Hello?
Hello.
I'm trying to correct your concept. I don't know I'm successful or not. Did you get it? Did I put in any current source in the circuitry? I didn't. I only say this portion of a transistor internal physical behavior can be electrically modeled by a dependent current source. Not a true current source, a dependent current source. It's a transistor's property, internal behavior. Okay? Hello?
Hello.
Yes, I'm here.
I think you're here.
Yes, I'm here.
Okay.
Okay. So once we model the transistor, the internal behavior between the base and emitter, we model that by a diode pointing from the base to the emitter. And we model from the collector to emitter by dependent current source. We have a circuitry configuration which we're ready to analyze. Okay, here the two bullets tells me how to analyze that. Okay, here I have two loops. If you're looking for the configuration, there's one loop involves the base and emitter. I call the BE loop, involves the base and emitter. And by Kirchhoff law, is the voltage VBB equal to voltage drop at the resistor RB plus the voltage drop at the diode. And then I rewrite this equation, I call the KVL, and I can figure out or calculate the base current. Once I know the bias voltage VBB, I know this. And KVL itself is not sufficient to solve the circuit. I have to use the device law. The first equation, I already used device law for the resistor. The Ohm's law here I use. So what I need is what? Device law for the transistor. And device law for transistor is between the base and emitter branch. And that when the transistor is full bias, that voltage drop is constant. So VBE equal to VBR. If I substitute VBE by VBR into the first equation, then I can figure out the IB, base current. So I'm combining the Kirchhoff law and part of transistor's device law, I'm able to solve the base current. And second, say, for the second branch, second loop, I can also write the Kirchhoff law, voltage law. Then it means the voltage rise, VCC, equal to voltage drop at the resistor RC, plus voltage drop between the collector and emitter VCE. So that's the second Kirchhoff law I write down here. VCC equal to RC times IC plus VCE. Well, I said before, at the first day of class, you need to combine the Kirchhoff law and device law. And here, the new device law is a transistor device law, which says IC equal to beta times IP, right? That basically tells me the dependent source here involved. And because I'm able to calculate the IB from the first part of the loop, I substitute the IB here, I can calculate the IC. And once I figure out the IC, I substitute into Kirchhoff law equation, then I can determine the voltage drop VCE. So I solved full circuit, transistor circuit. Okay. Here it just tells you how to analyze transistor circuit. This is still not the transistor circuit we see in the practical application. They just give you an illustration. Okay, how do you analyze the transistor circuit? Or how do you analyze the circuit where a transistor is placed in it? Any question? So this example is using the NPN transistor. And what happens if I use a PNP transistor? So the left-hand side is just a simple exchange of external power supply voltage flip the polarity and the direction current change. On the right-hand side is internal transistor, PNP transistor is modeled by between the base and emitter. Again, is a dial. Because the PNP, so it's pointing from the dial is pointing from the emitter to the base. It's a flipped direction again. Between the collector and base is another dependent current source. Again, the direction for a dependent source is the direction flip. So the external voltage now VBB flip the polarity, VCC flip polarity. Internal voltage drop. Now important things is because the PNP, so we care about voltage also VEB when it's off, and we care the external voltage is VEC. Measure that. Equation, you can say almost a side-by-side duplication. So let's just shrink this page. So shrink this page. This page. Okay, almost there. Yep. So I need to shrink this page slightly. Okay, so you can see the left is the NPN transistor configuration. We just work it out. And the right-hand side is the PNP transistor configuration. So you can see, because material region just changed from P to N, N to P, so the role of electron and hole exchange and all the current direction flipped and external voltage definition polarity also is flipped. But equation-wise, very similar, parallel to each other. Okay, you need a combination of the Kirchhoff law and device law to solve the full circuit. Okay, the Kirchhoff law, there are two loops in each example. The two loops involved. And one loop involves the base and emitter. I call the BE loop. Another loop involves collector and emitter. I call the CE loop. So I have one loop equation, I have another loop equation. I have one loop equation, I have another loop equation here. And derive the set equation. Okay, we have enough equations mathematically to solve the full circuit. Okay, so that's about subject that I want to cover today. Any questions?
Professor, I have a question.
Yes.
Do we get a formula sheet on the test, or do we have to memorize these formulas?
You need to memorize. But that sounds a little bit scary.
It's a lot of formulas, right?
Let me comment. That sounds scary because scary means we're involved the transistor. Transistor is much more complicated. The first exam is only on the dial. Dial only have a few formulas. So it's not as scary.
Okay.
Right. But the Friday, I can comment on which equations are basic. You need to memorize that.
Okay.
Okay?
Sorry for what happened with my voice.
Pardon me?
At the start of lecture, sorry for what happened.
Oh, but
mute.
it was fixed, right? So.
Yeah. I forgot to mute.
Okay, so that's what I heard some echoes and then from the student. Right.
Sorry.
Okay, no problem. Okay, any questions?
Thank you.
Professor,
Yes.
for the exam review on Friday,
Yes.
where do we go to attend that?
Huh?
How do we attend that?
WebEx. I will send an announcement. Okay, and then.
Okay.
Yes. Okay.
And I wanted to ask about discussion coming up. I think we all received an email from UMBC saying that because we've passed the 2 weeks in class, discussions can resume.
Mm-hmm.
However, I was wondering from you, what's the plan with that? Is it going to be this week? Is it
okay. You guys as a student and then so have to check your health situation. So you have a condition, and if they say 2 weeks and then no new positive or whatever situation occurred, that's the best news for all of you. But what I heard from the chair initially was we will wait for the UMBC COVID-19 team to tell us when we get clearance. So once we get clearance, then we'll go back to the in-person lab. And so far, I have not heard a word from them. So I'm trying to contact or wrote an email to the chair to basically try to follow up. Okay, he felt that we are ready, but I just don't know who will give the final say yes. So I don't know whether it's an instruction. Instructors can decide, or there's someone say divine chair say go ahead, right? So okay. I'm trying to. I don't want to make a mistake. Say no, they didn't approve, but I say go ahead. I don't want to do that, right? So that's this week is a little bit particularly sort of uncertain. So I instruct TA for this week. We continue to do the online lab. I think by next week we should get clear. Okay.
Okay.
Okay. Yeah. I hope TA should send you an announcement what to do this Thursday's lab. Yeah. Okay. Any questions?